The announcement of methane plumes on Mars has brought scientists to the brink of saying that, yes, there is life on Mars. But getting to this point meant putting together the pieces of an enormous puzzle. After those two little rovers confirmed that water had once flowed across the Martian surface, some big questions were raised. Could the ancient Martian oceans have supported living creatures? Could there still be pockets of water on or under the Martian surface where life could still exist? To try to find out, in 2006, NASA sent up a whole collection of instruments on the Mars Reconnaissance Orbiter. The MRO, as it's known, was fitted out with loads of extremely high-tech cosmic spyware, all focused on uncovering the history of water on Mars.
The way we do that is by looking at the shape of the surface, its morphology, how the layering is, the composition of the surface, and then we're probing into the subsurface to see what its structure is and whether or not liquid water might be present. At the same time, we're looking at the atmosphere, but we're looking at how water vapor moves in the atmosphere, and that's our common theme: follow the water.
In order to follow the water on Mars, the MRO has been fitted out with 6 principal sensing instruments.
What we're looking at here is the payload deck. This is our big telescope, the HiRISE instrument. This is a very high-resolution imager. This is the device where we get the best resolution, where we go in and look at the details of what's down on the surface. To see the area around it, we have the context imager. CTX, this instrument has a broader swath, lower resolution. It provides us that regional coverage. This instrument, the Mars Climate Sounder, is looking at how things change in the atmosphere over a full annual cycle in terms of what's the temperature of the atmosphere, what water vapor is there, what dust is blowing around in the atmosphere. Now we have another weather instrument. It's a camera, and it's looking horizon to horizon. This instrument is CRISM. This is our imaging spectrometer, and what we're doing with this is to look at the composition of the surface, because we want to see not only its shape, but what it's made of. On the backside of this spacecraft, we have another instrument, which is SHARAD, the shallow radar, which penetrates into the surface to look for layers of ice.
Here at Lockheed Martin Space Systems in Denver, MRO went from the drawing board to becoming a 2-ton reality. It took 5 years and hundreds of specialised personnel to design the orbiter and construct the instruments for its multi-purpose payload. The finer detail comes from MRO's eye in the sky. HiRISE, or High Resolution Image Science Experiment, is the largest instrument on the orbiter, weighing close to 150 pounds. It's the most powerful camera ever sent into orbit around another planet. Past Mars orbiters were able to identify a spot roughly the size of a dinner table, but from MRO's low-altitude orbit, HiRISE is able to detect an object about the size of a beach ball. One of the instrument's designers, Laszlo Ketsteyer, describes the level of detail HiRISE can achieve.
This rock here is about the size of rock we can reliably see with the camera on the Mars Global Surveyor spacecraft, and it's about 15 feet across, and it's a good-sized boulder. However, with HiRISE, we'll be able to detect the rocks that are about this size here. This is about 3 feet across. Now, one of the nice things about HiRISE is that it's taking these high-resolution pictures in color. We have a lot of science interests on Mars, but one of them in particular is looking at what water's been doing. When especially hot water reacts with rocks, it can change the rock's colors. So here we have a rock that's been altered to a red color with the hot water that's run through it. Hot water can do different things and change rocks to a green color as well. And so with HiRISE, we can see where the rocks have been altered these kinds of different colors and see what the water's been up to. And that should hopefully help direct future missions to the places where the water's been doing the most interesting things on Mars.
The HiRISE camera is photographing key areas of the red planet, but it's focusing its lens on only 1% of the Martian surface. It works in tandem with MRO's context camera, or CTX, which scans broad swaths of the surface at a much lower res than HiRISE, looking for areas that pique scientists' interests. On previous missions, CTX would have been the high-resolution camera.
This was the best resolution that we had.
Richard Zurich illustrates how the two cameras work together using a photo mosaic compiled from previous orbiters.
You had bright areas and dark areas, and we thought we understood what these things are, but when you look at it at greater resolution, suddenly you see what it really is. The dark spots are sand dunes, for instance. But the context imager is meant to get this over an extended area.
Once CTX identifies a target, HiRISE zooms in for a closer look. Up until now, you could only get this level of image detail from rovers, and they could only cover a tiny part of the Martian surface. The camera systems orbiting on the MRO can now generate high-quality images of virtually any point on the planet. But high-resolution cameras aren't the only tools in MRO's water-seeking arsenal. The Compact Reconnaissance Imaging Spectrometer, or CRISM, analyses light reflected from the Martian surface. Its sensors can literally see the individual colour components of light across the full spectrum, from visible to infrared. Since every mineral reflects a unique colour signature, CRISM is able to map the exact composition of the Martian crust. The spectrometer collects data in patches the size of a house to help scientists zero in on other rocks that have been soaked in liquid water and maybe even spot hidden hydrothermal deposits. And the Mars Reconnaissance Orbiter also functions as a weather satellite, letting us see for the first time in detail the forbidding weather patterns on Mars.
Our first emphasis is 1 Mars year of scientific observations. Why a Mars year? Because you get to see all the seasons. And that's an important climate signal that we're trying to capture. In fact, if there's one thing that we want to learn, it's how has climate of Mars changed over time?
The orbiter's Mars Colour Imager, or MARCI, acts as the spacecraft's meteorologist. This camera provides daily weather maps for the entire planet, just like satellites here on Earth, and it tracks environmental changes on the surface.
It's looking horizon to horizon so that you get an orange peel along each of 13 orbits a day, and when you put that together, you've got a global map daily of the weather on the planet, and then we monitor that for a full Mars year.
Keeping an eye on Mars's weather will help keep future missions to Mars safe and also help point them to potentially rich sources of liquid water. But perhaps the most powerful tool on the Mars Reconnaissance Orbiter is one that lets scientists peek underneath the planet's surface. Aboard the Reconnaissance Orbiter is a powerful new instrument called the Shallow Subsurface Radar, or SHARAD. It essentially gives Mars an MRI, allowing scientists to scan layer upon layer far beneath the planet's skin in search of water and ice that may still be stuck in the rocks below.
So far, we've been scratching the surface a few centimeters or probing only even microns. What your eye sees is just the veneer, just the surface of that. And now we want to get into that, but it's wide open as to what we're going to find.
The SHARAD instrument bounces radio waves up to a half-mile into the planet's rusty crust. Once analysed, the reflected waves can detect ice or liquid water in subsurface layers. Over the course of its first 2 years in space, the Mars Reconnaissance Orbiter has produced tens of thousands of images, maps and surveys above and below ground. More information than all previous Mars missions combined. Taken as a whole, the data tells a complex story of climate change and a history of watery environments that existed over the course of hundreds of millions of years. Some of them were just the kind of environments that could possibly sustain life. With data from the Mars Reconnaissance Orbiter, researchers were able to zero in on the very best spot to look for evidence of life-sustaining water. But could they design a spacecraft that could make a pinpoint landing and dig beneath the surface of Mars?